So hi everybody, welcome to Organ Technology Part 7. Now last time I promised we would take an up-close look at some of the relay components that go into both the pipe interface system that Rogers uses to mate their digital organs with pipe organs, as well as a traditional solid-state organ relay, which the basic principles have been the same for since the 60s, and they're a very reliable system, and they were used on both analog electronic organs and pipe organs. So let's get started. We'll first talk about the PIM. Rogers has a system for interfacing their digital organs with pipe organs called the Pipe Interface Manager, or PIM, and it's basically a programmable relay. And what happens is the console, when you're seated at a Rogers console, and this is true of other manufacturers' products as well, what happens is the console is sending out a data stream. Oftentimes it's MIDI or it's some other proprietary data system. But basically every keystroke, every stop on or off, every pedal, every move of the expression shoe is going to send out a data point. And then what happens is when we get into the pipe chamber, we want to route those data points to their appropriate locations. And so that's what we're going to look at today. So let's switch cameras and get over to the table, and we'll look at some gear, and I'll draw some pictures. Okay, so what we're looking at here is what happens after the data comes into the PIM, which is the box I showed you last time. And I also showed you some of these cards in situation. So we've got all these data points coming into the PIM, and then we want to route them over to wherever we need it to go inside the organ. This, of course, assumes that the organ has some kind of electric actuated valve system, Pitman chest, direct electrics, electric slider, what have you. Obviously, this will not work on a purely mechanical action instrument. But basically, the PIM is outputting a data stream that we have told when this comes in, we want that to go out. And so say middle C of the 8-foot principle, we want that to be pin number 25. And so we've told the PIM that by writing a plain text file using the right nomenclature and punctuation. And the PIM knows that when the stop 8-foot principle on the grate is on and I hit middle C, that it's going to be this particular pin right here that's going to light up, and then that's going to be attached to that particular pipe valve, and off you go. So in a unit organ, obviously we would have this set up where we would have a rank of pipes lined up. In a straight organ, we would have it lined up so that the key information was coming out and going to the primaries of the appropriate wind chest. So the Wicks organ over at Redeemer Lutheran is of course a unit organ. It's it's direct electric action. All the ranks of pipes are fully unified, and I'll refresh your memories on what that means here in a moment. And so we wired this up as if it were a straight organ chest, the same way you would either a Pitman chest or an electric slider chest. And the reason we did that is that we have to use fewer of these, and because the Wicks organ was fully unified and had a perfectly fine working solid-state relay system in it, there was no reason to do it differently. If we had done it where we had wired these cards, it would have directly into the pipe chest, it would have required a lot of extra wiring. We would have needed 5 or 6 of these cards. Instead, we used just 3 of them. It simplified the whole matter. And so that's what we chose to do. This driver system, basically it's both a decoder That's what these chips up here are for. And then a driver, these chips are amplifying the circuit. And they're doing that in much the same way that a standard solid-state relay system will do that. This is just decoding the data first and then sending it out, whereas a standard solid-state relay system is simply going to route it, one circuit per everything, and so we'll see how that works. But that's the driver card for the Rogers PIM. I'm not going to draw a lot of circuit diagrams because technically that's proprietary information, and because I work for the company, I don't want to get into trouble. Whether we're talking about an analog technology, electronic organ, or a unified pipe organ, we have to have the same kind of relay system to make it all work. In the case of an analog technology organ, you're going to have either a rank of oscillators, or say like this, and so let's say this bank of oscillators is meant to be a diapason. And so it's the oscillator filter is voiced to give them to produce an output that's a diapason. Well, my organ has to be connected, my keyboard has to be connected so that this can be the 8-foot stop, so it's going to be connected to the bottom 61. Or maybe I want it also to be the 4-foot stop, so I'm going to come up 1 octave, and I'm going to wire that. And then maybe I also need it to be the 2-foot stop, so I'm going to come up another octave, and I'm going to wire up the top part. In a straight organ, whether it be oscillators or pipes, you would have 3 separate ranks to be 8-foot, 4-foot, and 2-foot. Now, when it's separate ranks, it's a very simple wiring system. You just wire all the C's and then all the C sharps and then all the D's and all the D sharps and so on and so forth. And then you have a switch over here that if it's closed or open is going to allow those valves to work or not work. So when I select the 8-foot stop, this closes, and then I've got common going out and all these notes are going to play. Well, if I have a single rank of pipes or oscillators, then and I want that to play in a unit situation where I have the 8, the 4-foot, and the 2-foot borrowed from that singular extended rank, that's where the relay system comes into play. So here are our components. So we have to bring the keyboard in, and so that's what this junction is about. This is for a pedal board, so it's only 32 notes. So my key contacts from the pedal board are putting out, say, 12 volts DC, and they come into this card. We have some resistors on here to kind of limit the current so that the system doesn't get overloaded. And then we have a fuse here to protect it all in case it does get overloaded. And then that, clicks on here. And then all of these are wired in parallel. So all of these pins are connected, all the next pins are connected, and so forth. And so then each of these would be a relay switch similar to this. And the relay switches would all line up on here, and we would have each of our stops. You might have the 8-foot principal, 4-foot principal, 2-foot principal, and then the 4-foot flute and the 2-foot flute or something. And those would all have their corresponding relay switches. So when the stop switch on the console is activated for the 8-foot principal, this relay switch would be activated and it would send out a signal according to the keys. Then all of that has to be summed together over on what's called a driver card. And in this case, this is a really simple thing. The notes come in here, and I might have my 8-foot stop here and my 4-foot stop here. And then the pipes themselves would be driven over here, and I'll draw out how these circuits work in just a second. But we have these IC chips. They are basically what are called a transistor array, and they form with the other components an amplifier circuit. So the weak signal coming off of the switches is amplified up to where it will drive the pipes. And in the event that you have, say, just a straight rank intermixed with a lot of unit ranks, well, then you can have a card like this, and this is a combination card. It's both a stop switch and a driver. And so this has the same circuitry as this one here, but and this one together. So it's basically these two cards combined into one. So say on my relay system, I've got unit rank for the principal, 8, 4, and 2, and then I have a straight rank for the mixture and a straight rank for the 8-foot flute or whatever it happens to be. Then I would have these relay switches being wired over to the driver card for the unit stop, and then for the non-unit, the straight stops, I would have these cards, and they would plug in here and send the signal out that way. Just depends on what you want to do. So let me clear this off here, and then I'll make you some drawings and show you just exactly how this works. So really, a basic solid state relay system for an organ, for pipe organ or analog technology organ like a Rogers or an Allen, really couldn't be simpler. If you think about it, it's an AND function, right? If I play a key and I have a stop on, I need a particular pipe to play. So the way the stop switch works is by routing the signal either to ground or out to the driver. So we have a pair of diodes. And they come into a current limiting resistor, and one diode is sent through a switch to ground, and the other diode continues on to the pipe driver. And the way this works is when I have a keying voltage here, if this switch is open, that means the stop is in the on position, so the signal can't go this way. So it has to go out to the pipe. Well, this signal coming off the key, because we have several of these switches on every key, is not going to be strong enough. So that's where we need to go out to the driver. And the driver is nothing more than a simple transistor amplifier circuit. Now, obviously, this is, very abridged here. But the driver cards basically have a series of these simple amplifier circuits. There's a transistor, it's connected to source, so our weak signal comes in here at the base. We have our strong source signal coming in here at the emitter, or the collector of the transistor, and then the emitter goes out and gives us a boosted appropriate signal for the pipe valve. And that's pretty much it, over and over and over again. So you can kind of see this playing out here on this circuit. We have our resistor, we have our two diodes, and then we go, one of these diodes goes out, and the stop switch that's on the relay has the resistance source to control the current. And so basically, when this switch is in the off position, it is routing the keying signal as short to ground. And then when the stop switch is in the on position, that circuit is broken, so then the current is going to follow the path of least resistance or go on out to the driver, which is the transistor in this chip, and it's going to get boosted, and then it's going to get sent out to the pipe. And so it really just becomes a matter of wiring this thing so that you route the keying information, the signal coming in from the keyboard over to the correct location. And this is about as simple a way as you can do it. Now, if we look at this in practice, so we've got our unit rank of pipes. Well, you know, we'll say this is pipes. And then I'll have a driver card. And that's going to be our signal booster. And then I'm going to have a whole bunch of relay switches. One for every stop that is going to do something with that rank of pipes. And let's say, like we showed before, 8, 4, and 2 foot. And so what happens here is we wire this so that this switch goes to the top 61 parts of the drivers on the driver card. This switch goes to the middle 61, and this one goes to the lower 61, so that it corresponds to how our pipes are arranged on the wind chest. And then we can get the 3 stops out of a single rank of pipes. And these are all of the stop switches. All right. Now, if I have, say, this rank of pipes is going to speak on the grate only, I'm done, right? If they're going to speak on the grate and the pedal, which was a common practice with a lot of organ builders doing unit organs, well, on most pipe organs, we'd have to have a second set of switches for the pedal stops that we're going to pull off of that rank. And then those would also be wired into that same driver. So you have the outputs of all of these switches and these switches all summing up in the appropriate position on the driver card and then being sent out to the pipes. In Rogers analog electronic organs, they one-upped this. And then this is especially true on the smaller instruments. You would have a single switch for every 8-foot principal. We'll say this is going to be the diapason or principal. All right, so this one switch would be for both the grate and the pedal diapason. So would this one, and so forth. Well, how'd they make that work? Well, they time shared. So you have the keying information from the grate and the keying information from the pedal, and they're switching back and forth with a timeshare circuit. And so then you only need one of these switches. So if you dig into a Rogers analog organ, you will see a whole bunch of switches just like this one. It's a very similar circuit, but you'll only see one for both the grate and the pedal 8-foot principal. And what happens is there's an additional circuitry that routes the keying information from the grate and the pedal, and they're switching back and forth at a given rate. The other trick that can be done on the other end is that you don't really need a transistor driver to boost the signal. You're going right from the switch here over to the keyer for the diapason in the circuitry of the organ. And what happens there is that it too is switching back and forth at appropriate level. And you have a control inside there. You can adjust the keying voltage from the pedal and the grate respectively, so that if you want the pedal diapason to be a little stronger than the grate 8 diapason, you can do that. When you key the diapason from the grate keys, it plays at one volume, and when you key it from the pedal board, it plays at the stronger volume. And of course, obviously, if you play the same note on the grate and the same note on the pedal, whichever one is louder is going to win. But that was a way for Rogers to save on circuitry. But their analog technology organs use basically this same solid-state relay system, just like we've shown here. All you have to do is you've got your stop switch is being multiplexed on its input, and we're going right from here over to the keyer circuitry inside the organ. And so I think next time maybe we'll take a look at how this stuff works together in an older Rogers instrument and see how that worked out. So that's it for today, and I'm trying to get these out once a month. This one's a little late, but we'll try to be a little early next time. So thanks for joining me today. We'll see you next time.